Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're here to discuss the second homework problem of week 1. And the second homework problem asked you to calculate the interaction potential energy between two dipoles that are separated one from another by a distance of 0.5 nanometers. The strength of the dipole moment is given as 1 dBi, and the question is, what's the electrostatic potential energy that these two dipole moments will experience when they're this close to one another? So the first thing you have to recognize is that the direction of the arrow is also telling you the orientation of the dipole. It basically means that this end is negative, this end is positive, right? This end is negative, this end is positive. And since the polarity of the two charges closest together are opposite in sign, you're going to anticipate there'll be a net attractive interaction because this separation distance here will tend to win out over, let's say, the repulsive forces that are felt by the like charges. So you might expect just up front that this will be an attractive interaction. The electrostatic potential energy should be less than 0. To evaluate the electrostatic potential energy, we have to go to the lecture notes, and this is the equation that was given in lecture. The interaction potential energy is equal to the product of the two dipole moments divided by proportionality constant 4 pi epsilon naught. Epsilon naught is multiplied by the dielectric constant kappa of the material in which the dipoles are embedded. In the problem statement, the dipoles are embedded in vacuum, so that implies that kappa is equal to unity. And the most important feature of this equation is that the interaction potential energy varies as 1 over z cubed, where z is the separation between the two dipoles. There's a rather complicated geometric factor that has to be evaluated, and that requires you to understand the definition of these angles theta 1, theta 2, and phi. You have to apply that definition to this diagram. So the angles are measured with respect to the horizontal axis. So in particular, theta 1 is measured in this fashion. Likewise, there's an imaginary line from which you measure the angle theta 2. The angle phi is referred to as the twist angle, and if the two dipoles lie in the same plane, which they do in this case, phi is equal to 0. So that immediately tells us phi is equal to 0. Since the dipoles are oriented parallel to this imaginary horizontal line, that means theta 1 is equal to 0. Theta 2 is equal to 0, and that greatly simplifies the evaluation of this geometric factor. So we're in a position now to simplify this equation, right? So the interaction potential energy is minus the product of the dipole moments, P1 times P2. Cosine of 0 is unity, cosine of 0 is unity, so this is just 2. Minus sine of 0 is 0, so there's no contribution from the second term, right? This is 4 pi epsilon naught. Kappa is equal to unity times z cubed, right? So if we want to evaluate this expression explicitly, the minus sign comes through. We've got 2. A dipole moment of 1 dBi is equivalent to 3.33 times 10 to the minus 30 coulomb meters. That quantity is squared because the dipole moments in this problem are both equal to one another. 4 pi is 4 pi. Epsilon naught is 8.85 times 10 to the minus 12. And now we have to put in the cube of the separation distance, which in this case is 0.5 nanometers. That has to be cubed. So when I work all that out, I get a number that's minus 1.6 times 10 to the minus 21 joules. And that number matches choice D in problem 2. So the energy required to assemble these two dipoles is negative. That means that the dipoles will want to assemble, they'll want to come together in this configuration. And the magnitude of the interaction potential energy, the magnitude of the electrostatic energy stored when these two dipoles are in this orientation with this separation, that energy is 1.6 times 10 to the minus 21 joules. So that's how I think you solve problem 2.